Welcome to our unit on transformations. The first type of transformation that we'll specifically be focusing on is called a reflection. What a reflection does is it takes a point and reflects it over a line to give you a reflected point. Kind of like looking into the mirror gives you a reflected image. Except in geometry, we're not going to be dealing with faces and mirrors. We're going to be dealing with points that are being reflected over lines. So if we take, for instance, that blue point and reflect it over some line, the resulting reflected image would be, and I'm going to kind of ballpark it, but it would be somewhere around there where that red point is. Again, we would call the pre-image, the blue point would be P in this case, and the resulting reflected image would be P prime. The line used in the reflection, and this is going to come as a total shock to you because it's such a strange name for what it does, is the line of reflection. I bet you didn't see that coming. And the line of reflection acts as a mirror would. So there's a couple different kind of situations you can have when reflecting a point. More often than not, the pre-image point is not actually going to be on the line of reflection. Much like how when you look into a mirror, you are not usually on the mirror, unless you're doing something weird that we really don't want to get into at this point. But generally, you're going to see the pre-image point has some distance between itself and the line of reflection. If we were going to draw this out, we'd have maybe our line of reflection be something like that. We'd have our pre-image point, P, maybe be up here somewhere. And if we kind of sketched in a path from the point to the line of reflection, because points like to get places as fast as they can, we would find that a 90-degree angle, a right angle, would be formed between the point and the actual line of reflection. Furthermore, on the other side of the line of reflection, you would have another 90-degree angle, and you would also find that the segment to the point of reflection from the line is the same distance, it's congruent to the segment from the original point, the pre-image to the line. As a result, we could say the line of reflection is the perpendicular bisector of the segment from P to P prime. That's why this top segment and this bottom segment are congruent. The long segment from P all the way down to P prime is being chopped in half by that line of reflection. A much simpler case is if the pre-image point is actually smack dab on the line of reflection. So let's say there's our line of reflection. Our point P is actually on that line. That means to go from P to the line of reflection, you've gone a distance of 0, which means you have to go another distance of 0 from that point to the reflected point, which means you're not going anywhere. So P and P prime are actually the same point if P is already on the line of reflection. Sometimes you'll have to reflect an entire polygon. A polygon, remember, is just a shape. It's a shape with line segments, so like triangles and squares and rectangles and pentagons. Those are all polygons. If you have to reflect an entire polygon over a line, you simply reflect each individual vertex of the polygon over the line, and you will see the new polygon, the reflected polygon, form. For example, we want to reflect a triangle with vertices at these three points, 0, 4, 3, -1, and 3, -3, over this line y equals -x. So let's start by plotting the points. 0, 4 is on the y-axis, 3, -1 is in the fourth quadrant, and 3, -3 is just a couple notches below it in the fourth quadrant. And if I wanted to connect these to actually form a triangle, because it does say it's a triangle, now it's saying it needs to be reflected over the line y equals -x. That is actually in slope-intercept form. Slope-intercept form, y equals mx plus b. In our case, they don't really have a number in front of the x, so it's an implied 1. So really we could say y equals negative 1x plus, there's nothing there. Well, it's a 0. So the 0 is key because that is our y-intercept. We're going to start by plotting 0, comma b, which is 0, comma 0 in this case. That leaves negative 1 as the slope of the line. A negative 1 means for every unit you run, you go negative 1. It means you drop 1. So our rise over run is drop 1 and right 1. Drop 1 and right 1. Drop 1 and right 1. Oops, what did I just do? And if we want to connect, we want to actually draw this line in, y equals negative x goes through the origin and drops 1 block for every block it runs. We want to reflect the complete triangle by just reflecting the vertices of what we have. So to reflect, remember, reflecting a point, you want to go perpendicularly to the line of reflection. In this case, I went through 2 boxes, which means I'm going to continue 2 boxes beyond the line to get my reflected point. Same thing here, except I'm only going 1 box to get to the line. I'm going to continue 1 box through onto the other side to get my reflected point. And then lo and behold, this third point is smack dab on the line of reflection, which means we don't do anything with it. It's the same, both pre-image and reflected image are the same point. And we can draw in our reflected triangle and get something like that. Some kind of freaky mask looking thing, whatever. All right, let's take a practical application of reflections. Let's say we got this country road. And along that country road, somewhere there's a country house. We'll call this house A. And later on down that country road, there's another house. We'll call it house B. And let's say it's maybe the 20s or 30s, and electricity was just getting out to more rural areas. And the electric company comes out and says, hey, we want to put a post, an electric posts, we want to put a pole in the ground to hold up the electric cable that can run electricity to both of your houses. So I want to use 1 pole somewhere along the road that will have cables shooting off to both of your houses. But the electric company also wants to use as little cable as possible because cable isn't really, cheap. So they want to find where along the road they should put the pole to make the distance from A to road to B be the least, be the smallest distance. One way to do this, because we all know that the shortest distance between any 2 points is just a line. Unfortunately, we're not dealing with just 2 points here, we're dealing with 3. We need a point somewhere along the road. So one way to make these 3 points collinear would be to take point B, for instance, and reflect it over the road. Use the road as a line of reflection. So you draw a 90-degree angle from B to the road, and then go just as far onto the other side of the road, and you'd get a point. It wouldn't be B anymore, it would be B prime. This, by the way, would also still be a 90-degree angle. So now, instead of trying to go from A to B, let's focus on going from A to B prime. And oh my goodness, we have to cross the road to do that. I'll call that point P, where the path intersects the road. Because the distance from P to B prime is exactly the same as the distance from P to B. But what that tells me is that this point P would give you the shortest distance going from A to road to B as possible, and the electric company then could realize, all right, this would be the place we want to construct the electric pole. So to recap, reflections are just points, a single point or several points being reflected over a line. That line's called the line of reflection. Pre-image points might be smack dab on the line of reflection, in which case the reflected points are the same thing, or more than likely they are not on the actual line of reflection, and you have to construct, or you have to allow the line of reflection to be the perpendicular bisector of the original point and the reflected image. That's the gist. We'll be looking at some problems that deal with this directly and indirectly in the not so distant future.